This is a stochastic process module 6 martingales. Lecture 1 Conditional Expectation and Filtration. In the last 5 modules we have discussed stochastic processes, few properties, and then discrete time Markov chains and continuous time Markov chains. In this model we will discuss an important property of stochastic processes, martingale. In this lecture, conditional expectation, few important properties, sigma fields on omega, filtration, conditional expectation of a random variable, given sigma field, few important properties along with simple examples will be discussed. A stochastic process is often characterized by the dependence relationship between the members of the family. A process with a particular type of dependence through conditional mean known as martingale property. This property has many applications in probability. An example: a player plays against an infinitely rich adversary. He stands to gain rupees 1 with the probability P and lose rupees 1, it's equivalent of gain rupees minus 1 with the probability Q, that is 1 minus P. Let Xn be the player's cumulative gain in the first n games. The question is, what will be his fortune on the average on the next game given that his current fought? We need the knowledge of martingale to solve this problem. Martingale concept involves the conditional expectation of a random variable given sigma field. Hence, we will introduce the conditional expectation. Here is the definition of conditional expectation. Let x and y be two random variables defined on the probability space omega f p. The conditional expectation of the random variable x given the random variable y takes a value small y can be expressed in the form expectation of x given y is equal to small y. Both the random variables defined on the same probability space. Omega is the collection of possible outcomes, f is the sigma field, and the p is the probability measure. This triplet is a probability space. So, both the random variables defined on the same probability space, and we are defining the conditional expectation of the random variable given the other random variable takes a value small y. That can be defined in the form, if both the random variables are continuous, then we can make out as a integration minus infinity to infinity x times the conditional probability density function of the random variable x given that other random variable takes a value small y. Integration with respect to x, provided the probability density function of the random variable y at the point y has to be greater than 0. You know that the probability density function is always greater than or equal to 0 in the whole range of y. But here we are discussing the conditional expectation of x given the other random variable takes a value small y. So, at that point small y, the probability density value, density function value f y small y has to be strictly greater than 0. If that is the case, and we assume that here both the random variables are continuous, therefore we are having a probability density function, and integration is with respect to x multiplied by the conditional probability density function of x given y. Suppose both the random variables are continuous, then this conditional expectation of x given y can be expressed in the form summation xi's probability of x takes the value small xi given that y takes the value small y. So, this is a conditional probability mass function of the random variable x given the other random variable takes the value y. Here also the provided condition is provided the marginal probability mass function for the random variable y at the point small y has to be strictly greater than 0. In that case, you can find out the conditional expectation of x given the other random variable small y. Now, we present an example. So, here the omega consists of 4 elements A, B, C, D, and the sigma field is the power set. The omega is finite, so you can create the power set. The number of elements is going to be 2 power n, where n is the number of elements in the sigma omega. So, here the F is going to be the sigma field, which is the power set. So, that is the largest sigma field also, and we are defining the probability for each sample, that is 1 by 4, where W is belonging to omega. Now, I am defining two random variables x and y, satisfying the condition of a random variable, that is x inverse of minus infinity to x, that semi-closed interval inverse image is belonging to f for all x belonging to omega, then that is going to be a random variable. So, here you can cross check whether this real valued function x is a random variable or not. It satisfies the random variable condition. So, x is a random variable, similarly y is also a random variable. Now, I am going to calculate the conditional expectation of x given y takes a value small, y takes a value minus 1. So, that is nothing but the summation of a xi's p of x equal to xi given y takes a value minus 1. That means I have to find out the possible values of xi's, then find out the conditional probability mass function for those xi's, multiply it, then sum it over I, that is going to be the conditional expectation of x given y takes the value minus 1. So, the x can take the value 0, minus 1 or 1. So, I can compute the way minus 1 times probability of x takes the value minus 1, y takes the value minus 1. The next x can take the value 1 into probability of x takes the value 1 given y takes the value minus 1, 0 into the conditional probability you do not want to write, therefore, we have only 2 terms. Therefore, the conditional expectation of x given y takes the value minus 1, that is going to be minus times this conditional probability, you know how to compute, find out the joint probability mass function of x takes the value minus 1, y takes the value minus 1 divided by probability of y takes the value minus 1 plus the second term, that is a joint probability mass function of x takes the value 1 and y takes the value minus 1. You know the probability of x takes the value minus 1 and y takes the value minus 1, the only possibility is the sample is A, and similarly this sample is not possible, that is a empty set. Therefore, the probability of sample A, that is 1 by 4, the probability of y takes the value minus 1 is possible with A and B, therefore, it is of 1 by 4 plus 1 by 4, that is 1 by 2. Empty set probability is 0 and the denominator probability is 1 by 4 plus 1 by 4, that is 1 by 2. Therefore, simplification gives the expectation is equal to minus 1 by 2. Similarly, you can find out the conditional expectation of x given y takes a value 1 the same way. Now, I can write it in the compact form, expectation of x given y takes a value small y for all the possibility, that is going to be minus of if W is equal to A and B. This is going to be of if W is going to be C or D. That means based on the W, the value changes. W is nothing but the sample. W is belonging to omega. So the observations are, the conditional expectation is a function of y. The conditional expectation of x given y takes a value small y is a function of y. Not only that, the conditional expectation is a random variable, because for all possible values of w you will get a different values. Therefore, this is a random variable, whereas the expectation is a constant. Conditional expectation is a random variable. Few important rules on conditional expectation will be used to verify the given stochastic process has a martingale property. So, we list the rules. With the few assumptions, we have presented the proof, but these rules can also be proved without these assumptions. The rule 1 says, if x is greater or equal to 0, then the conditional expectation of x given whatever be the random variable y, that is always going to be greater or equal to 0. If x is greater or equal to 0 with the probability 1, whenever x is a non-negative, then the conditional expectation is also going to be a non-negative. That is a positivity property. So, the proof is given here. Assuming x and y are the continuous random variables with the joint probability density function f, I am going to give the proof. Similarly, one can give the proof assuming both the random variables are discrete random variables with the joint probability mass function also. Since x is greater or equal to 0, the probability of x is less than 0 is equal to 0, and the probability density function of x is going to be 0 for all x is less than 0. Hence, the conditional distribution of x given y, that is also going to be 0 for all x is less than 0, whatever be the y belonging to the real. So, when let y belonging to real, the conditional expectation is going to be minus infinity to infinity x times the conditional probability density function, and this conditional probability density function is going to be 0 for x is less than 0. Therefore, the integration exists only from 0 to infinity, because minus infinity to 0 the density function is 0. Therefore, the conditional expectation is going to be 0 to infinity x times the conditional probability density function. And you know that the probability density function is always greater or equal to 0 in the whole range, and x is here we are integrating from 0 to infinity. Therefore, this quantity is always going to be greater or equal to 0. So, this concludes, if x is greater or equal to 0, the conditional expectation of x given y, that is also greater or equal to 0. The rule 2, it is a linearity property. The linear property says the expectation of alpha times x plus beta times z given that y takes a value some small y, that is same as alpha times the conditional expectation of x plus beta times the conditional expectation of z, where alpha and beta are constants. It is similar to the linear property of expectation. The same thing holds good for the conditional expectation also. Therefore, no need to give the proof. The third one, that is the expectation law. Expectation of conditional expectation is same as expectation. It says the expectation of a random variable x can be computed in 2 steps. First, using the information on another random variable y, and next taking the expectation of the result. You can visualize in the other way around. Expectation of x can be computed as a expectation of conditional expectation of x given y. That means you can take any random variable y as long as the conditional expectation possible, find out that conditional expectation, then find, since the conditional expectation is a random variable, so find out the expectation of that random variable, that is same as the expectation of x. The proof is given with the assumption both the random variables are continuous with the joint probability density function f. So I am starting with the left hand side, expectation of expectation x given y, that is same as, you know how to compute the expectation. Here the provided condition is expectation exists. Similarly in the definition of conditional expectation also, you have to make the assumption the expectation is exist, then only we are finding the conditional expectation. So this expectation exists, therefore minus infinity to infinity conditional expectation, this is a random variable and you are finding the expectation of that, therefore you multiply the probability density function for the random variable y, because this expectation of x given y is a function of y, therefore you should multiply with the probability density function of y, integrate with respect to y between the limits minus infinity to infinity. And by definition the conditional expectation is nothing but x times the conditional probability density function, integration with respect to x between the limits minus infinity to infinity. So you substitute that, now you can come to the conclusion the integration of minus infinity to infinity, the joint probability density function of x and y is nothing but the marginal distribution. So here the integration is with respect to y, therefore you get the marginal distribution or marginal probability density function of x. So here it is a conditional probability density function multiplied by the probability density function, therefore this product will give the joint probability density function of x and y. Any two random variables joint probability density function can be written as the product of marginal distribution into the conditional distribution. So using that I am getting the joint probability density function. Now this integration is f of x, therefore the one integration and this much will give a marginal, therefore it is a minus infinity to infinity x times that is going to be the marginal probability density function of x, therefore you will get a expectation of x. So the right hand side is going to be the expectation of x. So you can find out the expectation of x by computing the conditional expectation with some other random variable, then find the expectation. So this rule has a lot of importance. The next one is independence law. If two random variables are independent, then the conditional expectation and the original expectation are both are same. The proof is assuming both the random variables are continuous, so the conditional expectation, this is by definition, and you know that both the random variables are independent, then the conditional distribution is same as the marginal, therefore you can replace this by the marginal distribution. So x times the f of x, that is nothing but the expectation of x. That means if the two random variables are independent, then the conditional expectation is not a random variable, it is a constant, because the right hand side expectation of x is a constant, therefore this is also a constant. The next rule is stability. Suppose you have the function g and the g of y is also going to be a random variable, that means g is a Borel measurable function. So the expectation of x times g of y given y, that is same as the gy will be out, gy times the conditional expectation of x given y. That means the later we are going to use the property called known is out. That means the expectation of x times g of y given y takes a value something, some small y, that means this is going to be treated as a constant. So, g of y has to be treated as a constant, therefore, the constant will be come out, therefore, g of y times the expectation of x given y. The same thing I have written as in the proof with both the random variables are continuous. Now, we introduce sigma fields on omega through an example, because this is very important concept for the Martingale. Example, start with tossing a coin infinitely many times. Tossing a unbiased coin infinitely many times. Let omega be the collection of possible outcomes HH and so on, HT and so on, TT and so on, TH and so on. Let F naught be the trivial sigma field, consist of two elements, empty set and the whole set. F1 is the smallest sigma field containing in omega 1. F2 is the smallest sigma field containing in omega 2. Containing the information learned by observing the first two consecutive tosses. If you observe, you will find the omega 1 contained in F1 contained in F2, F2 is contained in F3 and so on. Since we are tossing a unbiased coin infinitely many times, if you find out the limit of Fn that is going to exist, and that is going to be F infinity in the notation, and that in notation we can make out it is a F. So, this consists of the information learned by infinitely many tosses observation, that is the sigma field F. So, this is the way one can create the sigma fields on omega. So, omega is consisting of all the possible outcomes in infinitely many tosses, observation over the infinitely many tosses, whereas the omega 1 consists of only two elements. Therefore, we are creating a first sigma field on omega 1, and after you create four elements, the possible outcomes, after framing the possible outcomes into the four elements, you get the omega 2. So, using omega 2 we are creating a largest sigma field F2. So, like that you can create omega 3 F3, omega 4 F4 and so on, and all those F5s satisfies this property, and the limit exists as n tends to infinity. This sigma field is going to be denoted by the letter F. So, this is the way one can create the sigma fields on omega. Now, we present the sigma field generated by a collection of subsets of omega. Let U be a collection of subsets of omega, then the smallest sigma field containing U is called the sigma field generated by the collection U of subsets of omega. This is denoted by sigma of U. Consider an example where omega is equal to a comma b comma c. Let U is A. Then sigma of U is an empty set, element A, element B comma C and the whole set is the sigma field generated by the collection of sets A. Consider an example where omega is equal to A comma B comma C comma D. Define the random variable x which takes a value 0.5 for w is equal to A comma B. It takes a value 1.5 when w takes a value C comma D. Let A1 be the set which takes the value, which is the collection of possible outcomes in which the x of w takes a value 0.5. Therefore, it is A comma B. Similarly, let A2 be the set for the collection of w belonging to omega in which x of w is equal to 1.5. Hence, it is C comma D be the subsets of omega. Let u is equal to A1 comma A2. Hence, the sigma field generated by the random variable x, that is same as sigma of u, that is empty set A comma B is the one element and the C comma D and the fourth element is the whole set. Assume that for each t in 0 comma capital T, where capital T is a positive real number, then for each t between the interval 0 to capital T, you are creating a sigma field f of t, and those sigma fields f of t for possible values of t between the interval 0 to capital T, it satisfies the condition f of s is contained in f of t. If this condition is satisfied over the interval 0 to t by s and t, where s is less than or equal to t, then this collection of random variables, this collection of sigma fields is called the filtration. The definition of filtration in real time is as follows. In discrete time, the filtration is an increasing sequence f naught contained in f1, contained in f2 and so on of sigma fields, one per time instant. The sigma field fn may be thought of as a events of which the occurrence is determined at or before time n, the known events at time n. The natural filtration of a stochastic process xn is defined by fn is the collection of n plus 1 dimensional random variables belonging to B, where B is contained in R n plus 1. This is also written as fn is a sigma field generated by the n plus 1 random variables, or you can think of a random vector with the n plus 1 dimension. So, the fn is a sigma field created by the random vector x naught to xn, or the random variables x naught and x1 and so on till xn. So, this is the filtration in a discrete time. Let us generate a filtration for this example for discrete situation. So, take the same example, tossing a unbiased coin infinitely many times, and the omega 1 is having two elements. This is the sigma field on omega 1, and the f2 is a sigma field on omega 2, and also satisfied sigma f1 is contained in f2, which is contained in f3. Therefore, this collection of the collection of sigma fields is called the filtration. So, this is an example of creating sigma field in real time. To verify the given stochastic process has the has the martingale property, each random variable xt must be a ft measurable. So you will see the definition of when the random variable xt is going to be the ft measurable. For that, the definition is as follows: let ft be a sigma field of subsets of omega. A random variable xt is a ft measurable if every set in sigma field generated by the random variable x of t is also in ft. We have a non-empty set, that is a collection of possible outcomes, and we have created the sigma field on omega, and the random variable is said to be a ft measurable. The random variable xt is said to be a ft measurable if the sigma field, if every set in sigma field generated by the random variable xt is also in f of t. If this condition is satisfied, then this random variable is going to be called as a ft measurable. Obviously, f of t is contained in sigma of x of t. So here every element, every set in sigma field generated by the random variable xt is also in f of t. That means it's other way around. So if that property is also satisfied, then this random variable is a ft measurable. Some remarks on xt is ft measurable. The first remark: a random variable xt is ft measurable if and only if the information in f of t is sufficiently to determine the value of x of t. The f of t is nothing but the collection of the information up to the time t. So whenever we say the random variable is a ft measurable, if and only if the information in ft is sufficient to determine the value of x of t. The second remark: when a random variable xt is not a ft measurable, then the information contained in sigma field f of t cannot determine the values of the random variable xt. Whenever the random variable is not a ft measurable, the conclusion is the information contained in the sigma field f of t cannot determine the values of the random variable. Whereas xt is a ft measurable if and only if it has the sufficient information to determine the value of x of t. Third remark: if xt is ft measurable and g is a Borel measurable function, then g of xt is also ft measurable. We know that x is a random variable, then and g is a Borel measurable function, then g of x is a random variable. So here we are saying if xt is a ft measurable and g is a Borel measurable function, then g of xt is also a ft measurable. Obviously, g of xt is also a random variable. Since xt is a ft measurable, then g of xt is also ft measurable. The fourth remark: we are not giving the proof for these remarks. The fourth one: when ft is a sigma field of all subsets of omega, that is the power set of omega, and the omega is finite or countably infinite, then the random variable defined on omega is always ft measurable. Whenever the sigma field ft is the power set or the largest sigma field, in that case the random variable defined on omega is always a ft measurable. We know that whenever ft is the largest sigma field, then any real valued function is going to be a random variable. Here whenever ft is a sigma field which is a largest sigma field or the power set of omega, and additional condition, and omega is a finite or countably infinite, then the random variable is always ft measurable. Based on xt is ft measurable, we discuss adaptability of the stochastic process. The stochastic process xt over the t greater than or equal to 0 is said to be adapted to the filtration f of t if the sigma field generated by the random variable xt, which is contained in f of t for all t greater than or equal to 0. So, this condition is nothing but xt is a ft measurable. Whenever xt is ft measurable, then the collection of random variable x of t is adapted to the filtration f of t. If this condition is not satisfied, in that case xt is not a ft measurable. If xt is not a ft measurable, then the collection of random variables x of t is not going to be adapted to the filtration. Suppose it is a xt is a ft measurable. In such cases, all events concerning the sample paths of adapted process until time t are contained in f of t. It says f of t has the information up to the time t. Whenever xt is ft measurable, then all events concerning the sample paths of the adapted process until time t are contained in f of t. It is the same meaning here. The sigma field generated by the x of t, which is contained in f of t whenever the stochastic process is adopted. In a discrete case, we say that stochastic process x suffix n can take a value 0, 1, 2 and so on, is adapted to the filtration f suffix n. So, instead of f of t, I am using f suffix n for discrete type, and similarly the random variable is also discrete type. Instead of t, I am using small n. If the sigma field generated by the random variable xn, which is contained in the sigma field fn for every n, it has to satisfy for every n, then only this collection of this collection of random variable or this stochastic process is adapted to this filtration fn. For instance, suppose Sn is the price of a stock at the end of nth day, then the price process Sn, n is equal to 0, 1 and so on, is adapted to the natural filtration Fn, n0, 1 and so on, where Fn is the history up to the end of nth day. Now, we see the definition of a conditional expectation of random variable x given sigma field f. Earlier we have defined the conditional expectation of the random variable x given other random variable y takes a value small y. To the definition as follows: let omega s p be the given probability space, let x be a integrable random variable and f be a sub sigma field of s. So, here I am defining a probability space with the omega, and this is the sigma field s, and p is the probability measure, and the random variable which is integrable, and f be the sub sigma field of s. The conditional expectation of x given f. So, to distinguish the sigma fields f and s, I am giving the s is a sigma field and f is the sub sigma field, and we are defining the conditional expectation for the random variable x given the sub sigma field of s, that is f, that is denoted by x expectation of x given f it's a unique random variable. The way I discussed, the conditional expectation is a random variable. So here the conditional expectation of X given the sigma field, that is also a random variable. It's a unique random variable satisfying the conditional expectation of X given sigma field is a measurable with respect to the sigma field F. This is a measurable. Also, the integration over any set A where A is belonging to F, the expectation of X given F, integration with respect to the probability measure P, that is same as integration with respect to the probability measure P of the integrand is simply X, integration over A. Both are one and the same. Note that the conditional expectation given the sigma field F is a random variable satisfying these two properties. And we are defining the conditional expectation given the sub sigma field of S where this is the probability space. Notes on conditional expectation of X given the sigma field F. Note that the conditional expectation of X given F is a random variable while expectation X is a real number. Similarly, conditional expectation of X given other random variables also a random variable, not a constant. When F is the sigma field generated by Y, then we also write conditional expectation of X given F for the random variable X expectation of X given Y. Whenever F is the sigma field generated by Y, you can replace F by Y. Thus, expectation of X given F is the expected value of X given the information F. That means you can replace the random variable Y by F whenever the F is the sigma field generated by the random variable Y. That is same as the expected value of X given the information F. Whenever we say the sigma field, that is nothing but the information. We discuss the conditional expectation of the random variable given sigma field through two examples. The first example is as follows. Omega consists of 4 elements. S, that is the largest sigma field power set on omega, and the P of W's is equal to 1 by 4 where W belonging to omega. So therefore this is the set function probability measure. We are defining a real valued function. You can cross check, this is a random variable. Let F, that is a sigma field, it is a trivial one which consists of 2 elements, empty set and the whole set. Given F is a trivial sigma field, the only random variables which are measurable with respect to the trivial sigma fields are constant. The only random variables which are measurable with respect to the trivial sigma fields are constant. Hence, the expectation of X given the sigma field F, where F is a trivial one, that is same as the expectation of X, that is equal to constant. That constant you can find out by using the probability and the possible values of 0, -1 and 1, you can find out what is the constant. So here the conclusion is, whenever the sigma field is a trivial one, then the conditional expectation over the trivial sigma field, that is a constant, and that constant is same as the expectation of X, because it is no more random variable. The second example is as follows. Here the omega consists of 3 elements. S is the largest sigma field. Probability measure is defined on omega in each sample itself with the probability 1 by 3. X is the random variable. F is not a trivial one here. F is the sigma field, which is not a trivial one, and I am defining another random variable y, and that takes a value 0 or 1, and here I am claiming that expectation of x given f is same as expectation of x given y, because the y is the sigma field generated, because the f is the sigma field generated by the random variable y. If you create the sigma field generated by the y, you may land up a empty set, element A, element B and C and the whole set, and that is same as the f. Therefore, you can replace expectation of x given f by expectation of x given y. Here y is the f measurable. You can check y is a random variable also by finding the inverse images. The other properties are the first one, the conditional expectation is always greater than or equal to 0 if x is greater than or equal to 0. Then the linear property similar to the conditional expectation as I discussed earlier. Then this also I have discussed, instead of a sigma field I have discussed with the random variable. If they are independent, then both are same. The last two properties, if x1 is ft measurable, then the multiplication, the x1 taken out, which is what is known. So since x1 is known, because x1 is a f measurable, so x1 will be coming outside x1 times the conditional expectation. If G is a sub sigma field, then this expectation, conditional expectation, is same as the conditional expectation, and this is called the tower property. I am not going to give the proof of this. Here is the reference. Thanks.